Hello, my name is Roger Scheuer, and some years ago I invented a novel propulsion system which we called EmDrive. This stands for electromagnetic drive. It is in fact a propellantless drive. It does require fuel, but it is not reactionless and it is not magic. My objective is to pass on something like 20 years of acquired knowledge about EmDrive, basically before I forget it. And this, therefore, is a 5-day course of 10 lectures. My aim is to provide a detailed understanding of the physics, the engineering, and the applications of EmDrive. So EmDrive Basics is the first stage of what is a full design, build and test project. But first of all, we need to understand the physics of EmDrive. So this first lecture will concentrate on probably the biggest question that everybody has about EmDrive, and that is how it meets the law of the conservation of momentum. In lecture 2, we will look at how EmDrive meets the law of the conservation of energy. And in particular, we will look at the fact that EmDrive is a stored energy device and how this affects the conservation principles. Lecture 3 will cover the design equations needed to produce a cavity, a microwave cavity, which is the heart of an EmDrive thruster. And in particular, we will look at the design equations needed to design a tapered cavity. In lecture 4, we will then go through the cavity design process, which is an iterative process using an Excel spreadsheet, quite a large Excel spreadsheet actually. You will see as you go through this that an iterative process is absolutely essential for getting a correct EmDrive cavity. We will also look at the exercises that you guys can do using your own Excel spreadsheets, which you can develop and use to design your own EmDrive cavities. Lecture 5 will cover the tuning and testing of EmDrive thrusters. The tuning is particularly important because if you don't get it right, you will simply dissipate all your input power in the input circuits of the thruster rather than dissipating it actually in the cavity, which is what you need to do to get thrust out of the device. Now this thrust can be predicted according to equations, and then you can measure the thrust, and we will cover both prediction and measurement of thrust in lecture 6. The interesting thing is that if you are going to measure thrust on a static test rig, then you've got to get that right. Quite a few research groups have tried this and have completely failed to measure thrust because they don't understand the physics. In lecture 7, we will look at the technology development of EmDrive, and I will describe how we've gone from simple first generation thrusters through to quite complex fourth generation thrusters. And this has taken something like 20 years to get it all understood. Lecture 8, we will look at the mission analysis process, again using an Excel spreadsheet and basic simple equations of mechanics to be able to analyze, in the end, quite complex missions. We will select fourth generation vehicles for these exercises, which you can then carry out after you've developed your own Excel spreadsheets and come up with your own EmDrive vehicle mission analyses. In lecture 9, we will look at all the applications of EmDrive vehicles and look at some of the results of mission planning for these applications. Final lecture, lecture 10, will summarize everything we've learned. It will look at some future plans for, as I say, the design, build and test of a proof of concept thruster for you. We will look at future plans for vehicle development and production. And quite importantly, we will look at the implications of this, of these future plans. To help you understand what I'm going to be talking about in these lectures, I recommend these two textbooks, reference books. The first one, Microwave Engineering by Ritzy, is essentially a standard engineering textbook. It's particularly good because it covers microwave passive circuits and includes quite a lot of work on microwave cavities, resonant cavities. The second book, which is my own book, which was published last year, tells the full story of EmDrive. And chapter 1 actually goes back to the 1970s when I was working on a UK government project called Cheveline, and this was the nuclear warhead for the UK's strategic deterrent. And we were asked to look at alternative propulsion systems. We were particularly asked to look at what were then termed reactionless propulsion systems, because earlier, in fact, in Christmas of 1974, Professor Eric Laithwaite had suggested in a public lecture that gyroscopes could be used for propulsion systems. I worked for a company called Sperry Gyroscope, and we were considered the experts in gyroscopes. So we were asked to look at this and to actually think the unthinkable, which was marvelous. We were let loose to use our imagination, and we decided fairly early on that a mechanical system would not produce what the Ministry of Defence were looking for. But I put forward an alternative suggestion based on electromagnetic principles. This was not taken up, but it was looked at after I'd finished the project by Kent University. They looked at different versions of electromagnetic propulsion systems. And finally, in the 1990s, British Aerospace looked at it during their so-called Green Glow project. Meanwhile, I was doing lots of sensor work for mainly the British Army, and what this did was give me a very good grounding in the propagation, transmission and reflection of all sorts of waves, but mainly electromagnetic waves for radars and infrared sensors. I moved to the space industry in 1980s, and it was then that I realized that my early ideas for a propellantless propulsion system would be quite profitable for the space industry. And this led me to further considerations. So that's the introduction over. We will now start the hard stuff. We'll look at, in this first lecture, how EmDrive meets the law of conservation of momentum, absolutely essential law of physics. And the first thing to understand is that electromagnetic waves actually carry momentum. This doesn't matter whether they're traveling in free space or inside a waveguide. One way of looking at an electromagnetic wave is as a stream of photons. You can imagine these photons carrying energy, not mass, but modern physics tells us that energy and mass are equivalent. So you have a stream of these particles carrying energy, traveling at very high velocity, and they're therefore carrying momentum, such that when they are reflected, this momentum is transferred to the reflecting surface and produces a force which is classically called radiation pressure. A bit confusing because, in fact, if you look at the equation for radiation pressure, you will see that it is a force in newtons, F in newtons, which equals twice the power in watts divided by the velocity of light, c, in meters per second. So this is the force that an electromagnetic wave of power P would give for a reflection from a fully conductive surface, so that's perfect reflection, in free space. Now, to show that this force is real, satellite designers have to take account of the radiation pressure from the sun's rays. And on the Hotbird 2 satellite, which you can see in that photograph of the model there, you can see two additional panels on the solar arrays. And these are actually used to provide tiny torque to the satellite itself to enable the roll and yaw of the satellite to be controlled by the tiny forces from the sun's radiation. I've mentioned this because I want you to understand that radiation pressure is real and is used in space and is an engineering function that needs to be taken into account during satellite design. To look at EmDrive in detail, we need to look at it in terms of an electromagnetic wave rather than a stream of electromagnetic particles. So what is an electromagnetic wave? It's actually an electrical field E with a magnetic field H at right angles to the electrical field. And these two fields, which vary in time, also vary in space because they are traveling at a velocity which in free space is c, where c equals 3 times 10 to the 8th meters per second, the speed of light. Now, when the magnetic field H, which has a field strength B, cuts the conductive reflector at a velocity, it produces a current I, which travels along the conduction path in the reflector of length L. Now, there is a standard electrical machine formula which produces the force, where force is equal to B times L times I. Absolutely the heart of electrical machine design is F equals BLI. And it's interesting that back in the 1950s, a guy called Professor Cullen produced a paper which became the, if you like, the seminal paper on EmDrive. where he showed that the radiation pressure force equation F equals 2p over c can actually be derived from the machine formula F equals BLI. And this clearly shows, that the basic force mechanism in EmDrive is exactly the same as that of an electrical machine. The only difference is that the force is due to a radiated magnetic field rather than an induced magnetic field. So there's no magic to EmDrive. It's the same basic mechanism as is used in the electrical machines that really form the basis of the modern world. So now we look at what happens when you propagate an electromagnetic wave inside a cavity. And we've said that in free space the electromagnetic wave velocity is c, but inside a cavity this is reduced to what is known as the group velocity or the guide velocity. I think we'll carry on with the term guide velocity, and this is Vg as shown in the diagram. Now the wave will reflect off each end plate and therefore bounce backwards and forwards inside the cavity, and the total force, or rather the force on each end plate, will be reduced by the guide velocity Vg rather than velocity in free space. And the force is simply the same equation we used before, F equals 2p over c, but now we multiply it by the ratio of Vg over c. So this is the force at each end plate, and it's a symmetrical cavity, so these forces are the same, but they're opposite. And the total force that you generate inside the cavity increases with the number of reflections and is controlled by a term which is known as the cavity Q value, standing for the quality value of the cavity. Q can be extremely high. In the superconducting cavities of particle physics accelerators, for instance, the forces can be measured in tons, and this actually causes the cavity to stretch, and the frequency of the electromagnetic wave has to be altered accordingly. So we can see that there is potential here for very large forces to be generated. But in the accelerator cavities, because the cavities are symmetrical, the cavities won't actually move, they will simply stretch. So we've defined Vg as the velocity of the energy, momentum, and indeed the information in an electromagnetic wave when it's propagating inside a cavity. The important thing is that Vg decreases as the diameter of the cavity decreases, assuming that it's a circular cavity. And this decrease carries on until it meets what is known as the cutoff diameter. At this point, the velocity of the wave reaches zero, and the guide wavelength goes to infinity. Now you can see the effect on guide wavelength if you look at the diagram, which shows a large diameter cavity and a small diameter cavity. And you can see that the wavelength for Vg1 in the large diameter cavity is much smaller than the guide wavelength for Vg2 in the smaller cavity. So as Vg1 is greater than Vg2, the guide wavelength at Vg1 is much less than the guide wavelength at Vg2. Now, there are obviously equations which cover the calculation of both guide velocity and guide wavelength, and these are essential to the design of a tapered cavity, as you can imagine, which we will cover this in lecture 3, the design of a cavity. But an important thing to take from this slide is that the concept of cutoff. And this is real. We know it's real because in a microwave oven, the screen on the transparent door comprises a mesh of very tiny diameter holes. And the diameter of these holes are such that they're well below the cutoff diameter, and they prevent the microwave power inside the oven from leaking out to the kitchen. And if this didn't happen, I'm afraid we'd all be walking around with severe cataracts in our eyes. So cutoff is a real situation, and it's a situation that we must take account of in the design of an EmDrive cavity. Interestingly, the velocity of propagation, the guide velocity, it can be also decreased by propagating it through through a dielectric material inside the cavity. So if you fill up that circular cavity with a cylinder of dielectric material, then again the velocity, the guide velocity, will slow down. Now, a problem with this is that if you do use a dielectric material, and we have used it in experimental thrusters, unfortunately the losses inside the dielectric material are much more than the losses for an air-filled or a vacuum-filled cavity, and indeed it becomes impractical, we've found, to use a dielectric filling for a practical EmDrive thruster. The other important thing to stress is we've already said that as Vg decreases, the reflection force also decreases. So if you do reach cutoff situation, then the force at a reflector at this diameter will be 0. One thing that is unique about an electromagnetic wave is that it obeys the laws of relativity. Therefore, the velocity of the electromagnetic wave is fixed, and in free space it is a maximum of c, 3 times 10 to the 8th meters per second. If the electromagnetic wave is propagated inside a waveguide, or indeed inside a cavity, then we've said that the velocity decreases to Vg, but that Vg is constant and is independent of the velocity of the waveguide itself. So an outside observer will measure the velocity of the electromagnetic wave as Vg, not as Vg plus Vc. You can imagine the electromagnetic wave sliding along the inside walls of the cavity and therefore not affecting it. And another way of looking at it is if you take it to the extreme and you assume that Vg is close to the speed of light, as indeed it would be if it was a large cavity, and imagine the cavity itself is coming towards the observer at half the speed of light, then the velocity of the electromagnetic wave itself would not be 1.5 c. It can't be. Physics doesn't allow anything to move faster than the speed of light. What does happen to an electromagnetic wave in a cavity is when it is accelerated, then you get a Doppler shift in the frequency. And this will be looked at very carefully in the later generations of EmDrive. So you get a Doppler shift, but you do not get a change in the absolute velocity Vg. The important inference from all this is that the wave and the cavity therefore must form an open system, which allows the momentum to be transferred between the independent wave and the accelerating cavity. So maybe we should describe EmDrive as a relativity drive. So now we look at an electromagnetic wave which is propagated inside a tapered cavity, and tapered cavities are the heart of EmDrive. So as the wave travels down the tapered cavity from the large end to the small end, the velocity at the large end, Vg1, decreases until it reaches the small end, where its velocity is Vg2. And this diagram is actually taken from a design, a mathematical design of a cavity. And if you look at the guide wavelength, you can see that as it moves from the large end to the small end, so it starts to increase. And as you get towards the small end, you can see that the actual wave itself is starting to flatten out. So in a real design, and as I say, this is taken from a real design, at the large end, Vg1 approaches the speed of light, and at the small end, Vg2, it approaches 0. We've said that the force on the reflecting plates are proportional to the velocity, the guide velocity. Therefore, because Vg1 is going to be greater than Vg2, F1 is going to be greater than F2. And we have defined the thrust out of a EmDrive thruster as being F1 minus F2. But what does this actually mean? I mean, it's there, you can't avoid it, because the basic equations of microwave engineering say that F1 has to be bigger than F2. So what is the thrust? And the way to think of it is the thrust is the cavity itself pushing against the rest of the world, just as Professor Yang Jian said. There is a common misconception that in a tapered cavity, the difference between the end plate forces will be balanced out by the forces created at the side walls, the tapered side walls. Now, if there was just a standing wave in the cavity, this would be true. But the standing wave is due to a travelling wave going backwards and forwards along the axis of the cavity. And if you look at this particular cavity, which is a correctly designed cavity with curved end plates, you will see that the wavefront travelling close to the side wall is in fact travelling parallel to the side wall, and thus will produce no force. Whereas when it gets to each end plate, it is actually at right angles to the end plate at any particular point on the end plate, and therefore will produce maximum force. So in a correctly designed EmDrive cavity, the thrust is indeed the difference of the two end plates, and the sidewall forces can be 0. So now we get to the main purpose of this lecture, which is to look at the conservation of momentum. So first we'll look at it qualitatively and consider a cavity, a tapered cavity in free space. So it's now free to move. And we said that in this EmDrive cavity, the thrust will be in the direction of the small end plate to the large end plate. It's pushing against the rest of the world. Therefore, what happens to the cavity itself? Well, it's if you push against a brick wall, you'll fall over in the opposite direction. Therefore, the cavity will also accelerate in the opposite direction and will simply comply with Newton's third law. Thrust is in one direction, acceleration is in the opposite direction. Now, therefore, this means that because the thrust is in the direction small end plate to large end plate, then the net electromagnetic wave momentum is also in that direction. But because the cavity is accelerating in the opposite direction, the cavity momentum is also in the opposite direction. And you have the simple concept that the net electromagnetic wave momentum is balanced by the cavity momentum, and thus momentum is conserved. We will now look at the conservation of momentum in a quantitative fashion. But first we will look at the momentum balance of a simple photon rocket. This is an open-ended waveguide with a source of electromagnetic waves in the center. So we have source S, which is producing momentum m1 in one direction and m2 in the opposite direction. And indeed m1 equals m2. For this diagram, we will assume the vector convention of right is positive. If we define the total electromagnetic momentum as ME, you can see that ME is going to be M1 minus M2 plus M3, which is the momentum of the electromagnetic wave that's been reflected from the reflector R, where it was M2, and it's now coming out of the open-ended waveguide as M3. If we look at the momentum that is transferred to the rocket, mR, by conservation of momentum, mR plus me is equal to 0. Now, if we apply the convention, you can therefore see that mR is going to be equal to minus m1, m1 being equal to m3. So in this case, a simple photon rocket will accelerate in the direction of the net magnetic field momentum. So this slide is key to understanding the momentum balance in an EmDrive thruster. In the diagram, you can see we now have a tapered cavity with at the large end the reflector R1 and at the small end the reflector R2. In the middle, as before, we have the source of the electromagnetic wave. So, assuming that the velocity Vg1 at R1 is 0.9 c and the velocity at the source Vgs is 0.5 c and the velocity at the small reflector R2, which is Vg2, is equal to 0.1 C, then you can see that the momenta at these points, so at R1 the momentum is M3, M3 will equal to 0.9 M0, where M0 is the absolute momentum of the electromagnetic beam in free space. At the source, M1 and M2 will have absolute values of 0.5 M0, and at reflector R2 the momentum at this point, M4, will equal 0.1 M0. Now, if you simply do a vector addition of all these momenta to get the total momentum of the electromagnetic wave ME, you add them all up and you'll get that ME equals minus 0.8 M0. So we say that the momentum transferred to the thruster is equal to mt, and therefore by conservation of momentum, mt plus me equals 0, then mt will equal plus 0.8 m0. Therefore the direction of mt, and therefore the direction of acceleration, is large end to small end. Okay, so now we look at experimental methods of demonstrating the conservation of momentum in an EmDrive thruster. And I guess the first and obvious simple way of doing it is to place a thruster on an electronic balance, switch it on, and see if you measure any change in the weight of the thruster. Now, almost unbelievably, a number of research groups have actually tried to do this and expected to see an increase in the reading on the electronic balance when they put the thruster up in the direction shown in the diagram. This isn't going to happen. If you assume there's no thermal buoyancy effect and that the thruster weight is larger than the thrust itself, then the downwards thrust, which would be indicated by an increase in thruster weight, is simply counterbalanced by the upwards reaction force, exactly according to Newton's third law. So clearly, this simple experiment, which shows that you don't get any thrust out of an EmDrive thruster this way, is a good experimental demonstration of the conservation of momentum. In lecture 6, we will look at some of the correct ways of measuring thrust using a static test rig. But for the moment, we'll look at what I think is the ideal method of proving EmDrive does obey the law of momentum, conservation of momentum, by placing it on a beam on a rotary air bearing. The other side of the beam provides a counterbalance, and it is actually where we put all the instrumentation and part of the power supply. The idea is that the rotary air bearing gives virtually no resistance, and we will see later on that there is nevertheless a need for a very small amount of frictional resistance to get a successful start to the acceleration. And the idea here is you simply turn the thruster on, film the acceleration, then use the film to work out what the actual rate of acceleration is. And obviously we note the direction of acceleration. And from simply Newton's laws, where we've got mass and a measurement of acceleration, we can determine the value of thrust and then compare it to the static thrust that we measured previously on the rigs that we'll talk about. But the big thing to notice is that the direction of acceleration was large end to small end, as dictated by theory and as dictated by the requirement to comply with the law of conservation of momentum. The picture in this slide shows our demonstrator engine mounted on a rotary air-bearing test rig. The rig itself comprises, as we said before, of a beam mounted on the rotary bearing, and on one side of the beam we have the actual engine itself, and on the other side an instrumentation panel. Now, the total moving platform, the beam itself, weighed about 100 kilograms, so it's a very significant mass to actually start accelerating. And if you look at the demonstrator engine on the right-hand side of the moving platform, you'll see the large end of the thruster is pointing towards you. Therefore, for an anti-clockwise rotation, you can see that the thruster is actually accelerating from large end to small end. And we measured the acceleration by simply looking at the film we took, taking the data from that film, and the acceleration then was shown to comply with Newton's second law, force equals mass times acceleration. Now, in this case, the force is the thrust minus the air-bearing friction. Before each test run, and we did quite a few of these test runs, the actual air-bearing friction was measured by the simple method of using weights on a weight pan attached to a piece of string over a pulley wheel. I mean, very simple, but actually a very accurate way of measuring the air-bearing friction. The test results for the test that we quote fairly widely, which was number DM188, was a maximum thrust of 96 millinewtons, giving a maximum acceleration of 0.042 centimeters per second. Not a very large acceleration, but significant when you look at it over an acceleration period of a minute or so. The friction force involved was 54 millinewtons. The power we were putting into the thruster itself was 334 watts. Maximum velocity we achieved was 2 centimeters per second. And the total distance we flew, because we like to think that it was actually flying on the air bearing, was 185 centimeters, which is a couple of rotations of the test rig. Now you can actually see this, the film of this test on our EmDrive.com website, and you need to go to the development page and look under dynamic tests. This particular film of DM188 was shown to government agencies both in the UK and the US, and certainly the US Air Force declared this as proof of concept for EmDrive.